linear regression from Skyfi Labs, and we have prepared a price predicting model for the Boston housing data that is present in the sklearn dataset. So first we need to import some libraries such as NumPy and Pandas. Matplotlib helps us to plot graphs, and the sklearn library have functions like mean squared error and min max scalar and the functions for splitting the data. And we'll also import IPython display HTML for animation of the training model of the data that we are training. So first we need to load the data. The data is called Boston, and we can just load it with the command load underscore Boston. And if we use the descr command, then we can get an output of the number of attributes that are present in the database, which are generally the features of the database from which we can predict the prices. So here we have 13 attributes and a median value, which is the 14th attribute. So now we will just use the data frame object present in the pandas library to assign the features column from the Boston data to a features array, to a features data frame, and then we can print it and we can see the result. There are 506 rows and 13 columns, which are the 13 features and 506 values. We can also use commands like feature and then call a separate column like NOx, which is the nitrogen level, and we can see the values. Now we'll assign the target, which is the prices we need to predict, which are the prices that we need to predict, and we can use the data frame object present in the pandas library here to assign the target column, and we can check and print it. We can also use functions like min and max here to print a minimum and a maximum value for a feature like target here. Now we just need to concatenate the features and the target into a data frame. We can just use the concat function of the pandas library, and the axis equals to 1 denotes the column wise concatenation. Here the default is axis equal to 0, which is a row wise concatenation. We can also use the describe data frame object to describe the mean, the standard deviation, the count, min value, the percentile, and the max value, which are all displayed here for particular columns. Now we just need to find the correlation between the target value and the features. Correlation is just a dependency rate of a feature and a target. How the change in a feature depends on the change of the target. Here we can use different type of correlation, but we are using Pearson's here. So we can just and we also will obtain absolute values for every attribute in the list feature, and then we can just zip them together in a list with the features and correlation value. Then we'll sort them and then unzip them again, and we can just use the matplotlib library to plot the graph against the attributes and see how they are dependent. We are taking the absolute value, so we'll get all the positive graphs, but if we remove the absolute function, we can plot the graph in which we have negative values and positive values for the correlation between target and attributes. We can see that lstat is an attribute on which the target value depends inversely, and the rm is the attribute on which the target value depends highly positively. Then we need to normalize the data. We'll use the LSTAT feature because the target value is affected by it the most from all the attributes, and then we'll use the target column for the Y. And then we can normalize the data using the min-max scalar object and create an instance and use the fit transform function. We use the reshape function because the fit transform only allows vertical data, and then we can use slicing to change it back. Then we need to split the data into testing and training data. We'll take 80% of the data as the training data, and we'll take 20% of data as the testing data. Then we need to define some kind of a cost function. Here we are using the mean square error function. We need to define 3 functions for it to run. We will define error to find the mean square error. We'll define update to update the MNC slope for the linear regression equation using the update function, and we'll define the gradient descent function in which we can use the number of iterations to run a loop and check for error every time the M updates. After the error is less than the error threshold, we can break out of the loop and then save all the values in error case and return the final MNC value for the prediction. Here we use the gradient descent function, keeping the learning rate at 0.001, and after running the gradient descent function for training the model on the training data, we can plot the regression curve, which is the training data and the prediction values. We can see that the slope of the curve is negative because the LSTAT feature we use for the training model has a negative impact on the target value. We can also see the errors with the iterations, and we can see that the error have gradually decreased over the iterations, and we can also visualize the training phase of the model by using the HTML and the func animation objects. We can see in this video how the model trains itself and the regression curve changes accordingly while the MNC change. And now we can get the predicted values using the y equals to m into x plus c equation of the linear regression. We can also test the mean squared error against the target value and the predicted value, which is 0.0158 for the LSTAT feature, and then we can just add the testing data and the predicted value in a data frame and show them, and we can also plot the scatter plot of the testing data and the target value and a line for the predicted, and we can see the results. Also, we need to find the predicted data in target values. We have the predicted data in a normalized form, so we need to revert the normalization by scaling it. We can use the inverse transform function for it, and then after scaling we can just put it back in the data frame and just show the values of the target value, which is the y-test, and the predicted value. We can also change the feature to RM to test out a feature which affects the target value positively. We can just change there and run all the cells below and see the result. We can see here that the graph for the regression curve after training and the slope here is positive because RM affects target values in a positive way. This is the error graph curve, and we can see that the model now has changed its direction and the slope is positive. The mean squared error here is 0.02, which is approximately 2 times the mean square error for LSTAT. We can also change the training feature to something which affects the target value at a minimum rate, as CHAS is a dummy feature. We'll use this. Then we can change it here and run all cells below to see. After the training of the data has been done using the gradient descent function, we can see the slope and the values are scattered around the map because the target value is affected less by this feature. Also, the mean square error, which is 0.043, which is approximately 4 times the mean square error found when using LSTAT. And these are the predicted values for the feature disk after using it.